Hello people, I'm Tom Heats, welcome on my channel, and today we're going to cover the topic Bitcoin blocks. So let's dive into Bitcoin blocks and what components it actually consists of. So at first we have the magic number, and this is just a usual number which will always stay the same. This is 4 bytes, and if you're not familiar with the term magic number, it is just a number which describes the type of data we have to deal with. So for example, for DHCP, GIF, JPEG and PNG, you have those numbers. For Bitcoin, we have our own number, and this just describes which type of data we have to deal with. And next up, we have the block size, and this just describes the size of the current block, and this is 4 bytes. Next up, we have the block header, and the block header consists of 6 items, which I'm going to cover later on, and the block header is 80 bytes. Then we have the transaction counter. This is just a positive integer, and it describes the amount of transactions we currently have in this block. Of course, if there comes in a new transaction, then the transaction counter will increase, and the transaction counter is usually between 1 and 9 bytes. And last but not least, we have the transactions, and this is just a list of all the transactions which are in the current block. And yeah, approximately there are 3,500 transactions in a block. So not bytes, these are transactions. If you have a given 1 megabyte block limit, of course with SegWit these transactions can increase. If you want me to make a separate video about SegWit, just let me know this in the comments. Next up we have the Merkle Root, and I have to cover this before we actually go over the block header, because there's some important information you may not know, but you needed to understand the block header. And the Merkle Root hash is at the top of the Merkle tree. So this whole thing here is a Merkle tree, and it results in a Merkle Root hash. And how is it calculated? Well, you take all the transactions you have in the current block. You just take all of the hashes. For example, for transaction A, you have a hash. For transaction B, you have a hash. You hash them together. You have a subtree B. You have a subtree C. You hash them again together until there is only one hash left. Then you take the Coinbase hash, and this is just the hash of the Coinbase transaction, which the miner create when they actually create a new hash. And this, the Coinbase transaction has no inputs but an output to the miner address. Then you hash those two together and you get a Merkle Root hash. And this is included in the block header, which I'm going to cover now. And last but not least, we have the block header. The block header consists of 6 items. At the top we have the version. This is just the version of the current block. If this version is below the needed version, then this block will be recognized as invalid. And this is 4 bytes. Then next up we have the previous block hash. This is just the hash of the previous block header. So you take all of the components which are in the header, hash them, insert it here. And of course this makes the blockchain a blockchain because the actual blocks are connected with each other. So if you change any component of the header, for example if you just add a new transaction or something, then the hash will change, and the next hash will also change because there's always a field with the previous block hash, and this connects the blockchain. And it is 32 bytes. Then we have the Merkle Root hash, which is also a 256-bit hash, and you might know this now because I've covered this just before. And this is also a 256-bit hash, and it changes every time a new transaction comes in. Of course, I think it is pretty easy to understand if you just think of the whole Merkle tree. If there is a new transaction, then the whole computation would be different, and it will also result in another Merkle Root hash. and this is 32 bytes. Then we have the time. This is just a timestamp. It updates every few seconds, and this is 4 bytes. And then we have the bits, which is a compact format of the target, and this number must be lower or equal to the target. If it's higher, well, then the block will be recognized as invalid. This updates every time the difficulty is adjusted, and also the bits is 4 bytes. Last but not least, we have the nonce. It is just a 32-bit number, a positive integer which starts with 0, and this is needed for the proof of work algorithm. If you take, for example, the previous block hash and the Merkle Root hash them together, you add the nonce. For example, if the nonce is 1, you add the nonce. And if the difficulty says, for example, we need a hash starting with 4 zeros, if the hash with the nonce, the root hash, and the previous block hash is not starting with 4 zeros or even 5 zeros, well, then we need to increment the nonce by 1. So now the nonce is 2, we hash them together again, check. And so it goes on and on and on. And finally, when the nonce is something around 2 million or something, well, it depends. It could also be 5 or something. The block will be valid and the nonce will be included in the block. And of course, that is just a very big advantage of a hash function. If you have the given inputs, you can create the same output. So it's easy to verify if the nonce is given. We can just check, okay, this block is valid. This results in a valid hash, and the block is appended to the blockchain. So I hope I was able to describe the Bitcoin blocks and you were able to follow me. If you like this video, I'd be glad if you gave this video a thumbs up. If you're not a subscriber, I would encourage you to subscribe to this channel, and see you next.